Okay, it's after 4 o'clock, so I think we can get started. Welcome back, everyone. So today is the final lecture of actual content. The next lecture is going to be final review. Today we're going to be going over stack smashing. This is not going to be on the final. This is just something for your own edification and something interesting you can find that we can do with the information that we've learned so far in this class. One thing I want to reiterate just at the top here before we begin, just make sure that for the final you're studying more than just that example we did last time. Make sure to study the homeworks. I'll be going over this again in the final review day, but that is a good example. It's a pretty complete example, but the final has many questions on it, so just make sure to study more than just that one example. Okay, any questions before we begin for the day? Yeah.
How representative of the final are the most recent spate of projects going to be? Is there going to be a lot of translating between simple IR and C# and C++ ongoing?
Well, we're not translating from C++ to simple IR.
Right.
So I think you mean translating simple IR to assembly.
Yeah.
There will be questions about translating simple IR to assembly, I'll tell you that.
Okay.
And questions about understanding how assembly code works, and maybe even going backwards from assembly to simple IR. So this is really just to evaluate your understanding of what the semantics of these two languages are and how they connect to each other. So you should know that, because in order to implement the compiler, you have to understand the underlying semantics of simple IR and how to convert that meaning in simple IR into the corresponding assembly code. So if you're able to do well in the projects, then you should have an understanding of how to translate between the two languages, or at least what different constructs correspond to in those two languages. Okay, so before we begin for the day, let's look at the homework. What can happen to the return address by the calling function if an array stored on the stack is overridden while past its bounds? That's the topic of today's lecture.
Honestly, I'm low-key confused on this because I don't know if this is dumb, but I thought that arrays pointed only to the first thing, so if it was super overloaded or whatever, it wouldn't impact the return address, it would just impact it itself. Does that make sense?
So an array is a pointer. It points to the first element of an array, typically. But arrays have a size, correct? And what direction does the stack grow? Down. Arrays actually also grow, arrays grow upwards. So I didn't disclose that in the information here, but if we assume that overriding the bounds of an array and it grows upwards closer to the high address, what also is closer to the high address? The return address. So if we're, yeah.
Would it just straight up delete it then?
Well,
Would it just be junk memory or something?
it could be junk. In the most harmless case, the return address is overridden with some invalid address, and then when you try to access it, what kind of fault will you get?
Segmentation.
A segmentation fault, segmentation violation. And your program will just crash. But in a bad case, you won't get a seg fault, and your code might actually, your program might start executing some code you didn't intend for it to run. And in the very bad case, it might be nefarious code, malicious code that was injected by an attacker. And today we're going to see how you can actually inject some malicious payload into a program by overwriting or overreading input into an array, past the bounds of an array.
Are there any automated checks it doesn't allow you to write an array of such size?
Automated checks for allowing you to write what are you actually asking for to be automated?
If you're going to allocate an array of size n, does it check to see if n is smaller than a certain number that would have overwritten the return address?
Well, it's not the array size that's overriding the return address. It's what you're writing into the array. So we'll see some examples of this shortly. But the big idea is if you have an array of size, maybe, 4, and you try to read 5 bytes of information into it, the 5th byte is going to exceed the bounds of the array. Now, a higher level language like Python or Java will tell you an array out of bounds exception has occurred. That's because they insert dynamic, by dynamic I mean they're executed at runtime, dynamic checks to make sure that the index you're trying to access does not exceed the bounds of the array. But C, because C is so focused on performance, does not perform these sorts of checks. It eschews them in favor of higher performance. And so you're allowed to write potentially to an address or or an index exceeding the bounds of the array. And there are ways to check for this. You can run your C code, run it with tools like ASAN, Address Sanitizer, or Valgrind. That's another popular one. Purify is another C program you can use, or another program you can use. And these programs sort of wrap around your C code and run it, and will tell you if there's a memory leak or an out of bounds memory access or anything like that. So I'd recommend probably learning how to use Valgrind. That's the one that I like to use sometimes. You won't see it today in this lecture, but I recommend looking into this tool a little bit. You might find it helpful, especially later in your CS degree. You might be asked to do a project where you have to report memory usage of your program, and Valgrind can do that for you. So, or help you with that. Okay, any other questions? Yeah.
Is it possible to, like in, I learned this recently in Java, but like, is it possible to like catch, like, what would be like the error that's caused by this? Like,
Out of bounds.
yeah.
So you could write your own list function, your own list data type, your own list struct, and you could define your own functions for appending to that list or retrieving a value from that list. But then you have to write your own functions for wrapping around basically just array index accesses. And then you get a safer program, but you also now have a little bit of performance penalty for incurring this check every time you go to access an element in the array. Yeah. So, I mean, the age-old adage is whenever you have a problem in C, the solution is to just write more C. And the same applies here. Okay, so let's look at the page for stack smashing. It's actually a very short page, very short set of notes. The first note here, the first link, is this classic article on stack smashing by this programmer, Aleph1, this cool, like, I don't know, gamer tag sounding name. They're actually a Venezuelan programmer. I forget their name, Elias something. Aleph1. Or no, this isn't it. That's not it. All right, well, I'm having a hard time finding it, but you can find the name of the individual behind this article. It's actually a very famous article in like hacker communities because it's really the first well-written article explaining how to do stack smashing. And even though it's like pretty old, I don't know exactly how old this is, but you can tell it looks pretty old. And all the diagrams are like text. It's actually very well written, and especially the first like third of the document. I think based off what we learned in class, you could all read this and fully comprehend it. Some of the register names are a little different because they're dealing with an older version of x86, but they focus specifically on x86 Linux machines, which is exactly what we're studying in this class. And they show how to basically smash a stack, overwrite the return address of C code by exploiting the stack in this article. So yeah, I'd recommend checking this out, maybe reading just at least the first like third of the document, just to test your understanding of the class material. It's pretty interesting. And then for us today, we're going to be actually following this tutorial to smash the stack. I've condensed the instructions into a README document, a markdown file that we're going to be following along with. And if you'd like to reproduce this or follow these steps along yourself, you can clone the GitHub repository that my advisor has made for performing the steps that we are going to be going over today. And also there's this website here I recommend, pwn.college. It's pretty fun. It's like a bunch of little games you can follow to learn how to hack things. Okay, so any questions? That's so much for the homework and prologue.
Is this only possible in C?
Stack smashing? I don't think so, because we're exploiting the ABI, and other languages will compile to the same ABI if they want to have interoperability with C. Now granted, other languages might have other mechanisms in place to help prevent this from being possible, But if a language doesn't have bounds checking on arrays, then I think it would still be possible to do it in that language. It should be. Okay, so to sort of explain the intuition of what we're going to be doing today, let's look at an example. Let's assume we have the stack here on the right, and we're going to be looking at some C code, not assembly code, not simple AR code, but just some sample C code here. We'll assume that the base pointer is stored here, the return address is already on the stack, and it's set to this arbitrary value, hex EF7. Just some random value that I picked, just for the sake of this example. So if we were to go through this code normally, step by step, the user will read some value into the variable y. So we'll say the value 2. Let's just assume that's what's read into y. Set x to 3. And then declare an integer array of size 3. And the way arrays are going to be laid out in memory is that they are set, the starting point of the array is at the lowest point in the stack for which the array's bytes span. And then the array's indices go upwards towards the high address. And my intuitive explanation for this is that we index arrays by positive values, and positive offsets will go higher in the stack. So that's why my best guess as to why arrays are laid out in this way in memory. So index 1 would be one positive offset higher in memory, in the address space, which would be lower on the stack. So in the next line of code here, we're going to set the value at index 2 of the array to 1. And then set the value at index 0 to 2. Print the value of the array. And then set array y to 0. So what is the value of y? 2. So we're going to go to 0, 1, 2. And place this value here. So we'll set this to 0. So does that make sense? That simple trace? It should be hopefully pretty easy to follow along with. So what happens, let's go back here. What happens if instead of having y set to 2, we had it set to a value like 6? One, 2, 3, 4, 5, 6. So now we've changed, yeah.
Or you never mind, 7.
Okay. Now we've changed the return address to 0. And that should give you a segfault. Yeah.
So the objective is to make the return address, if you were hacking maliciously, hypothetically speaking, then it would be to make the return address be to where your code is?
Yes, yes. Either some code already in the program that you want to run in out of order, in some order that you want to run it in, or you could inject, and we'll see how to do that shortly, you could inject some malicious code yourself and then actually have the return address jump to the code that you inserted. Okay, any questions? All right. So what we're going to be doing, what we're going to see what you can do to smash the stack, is we're going to take this array and we can overflow it with too many values here, past the bounds of the stack and even past the return address itself. So normally you might not have, well, if you're trying to exploit a program, you probably won't have a situation like this where it's so clean that the index is what you can modify, letting you overwrite a specific value in memory. Normally what happens is the user makes a call to read, which I don't know if you all remember the read system call that we saw before. So I'll open the man pages here. The read sys call accepts a buffer as its second argument, and that would be ARR in this case, that will be our buffer, and then a count. So a number of bytes we want to read into the buffer. That's normally what you'll see in an actual C program, some call to read or some other call like syscall like that, or functionality similar to read. And so with that, we can actually read a number of bytes exceeding the bounds of the array. So it's a little bit different. We're not injecting a specific value at a specific index. Instead, we're just reading past the bounds of the array, overwriting everything in its path, in our path, and eventually overwriting the return address along the way. Or, yeah, the target is a return address. We're overwriting other stuff on the way to get to it. And one thing I want to point out is that this doesn't just apply to local programs running on your own machine. A similar idea also applies to programs on the internet. So let's say you have some program or some website you're trying to access on your machine, and you go to an Apache web server. Your request gets routed to an Apache web server. UCF's web servers use Apache, or they are Apache web servers. And the Apache web server reads in some packets that are sent across the network. It probably has some like TCP or ICP socket open for reading. And if this web server has an overread or reads too many bytes, you could possibly exploit that machine and then get full access to whatever is on that machine. So in the case of the UCF web server, you could get access to the grading scripts for this class, for instance, and see all the answers to the homework solutions. Granted, I don't think there's any bugs in Apache that you'll be able to find very easily, but yeah.
This is like a hypothetical, but like in a class like this, wouldn't it be like a good thing if you were able to do that? Like,
It would be cool. Yeah, it wouldn't be cool if you did it and then shared with the rest of the class. If you did it and then told me privately, I'd probably give you extra credit or something. Also, you probably want to submit a patch to a bug request or a bug notice to the Apache maintainers. Yeah. I'd be very curious to see how you did it, but yeah. So, and again, in other contexts, we have our programs that we wrote, so on our own machines, the MyShell program, how we're reading from standard in. This is another situation where an overread can occur. You can overwrite the stack because you're letting the user read some values into your program. Really, wherever there's this issue of memory being read in, whether it be in the internet or on your local machine, you always have to worry about this read overflow issue occurring, or write overflow, depending on how you want to look at it. So what we're going to be doing to actually exploit this vulnerability is we're not just going to be writing garbage into the program, we're going to be writing a whole payload that contains an overwritten return address along with some malicious code that we're going to be inserting to actually run bin.sh, which is going to be the shell on our machine. And we're going to modify the return address to actually jump to the code that we've injected as part of our payload. So we're going to contain both the modified return address and the entry point of the malicious code that we've injected. So I understand maybe it's a little confusing. Two things are in one here. But any questions or? No. Yeah, in the back.
So are we using input to do this, or are we directly injecting it to a compiled program?
So the program's already running. It's already been compiled. And then we're going to feed it an input that achieves this exploit.
Aren't most in most modern IPs, don't they use, and like IRC standard, don't they use like a different version of input that prevents overflow?
So they don't use a different version of input, but there are some mechanisms for improving the security of the program that we're going to have to disable for this example to work. And back when this article that I pointed out here was written, I don't think these mechanisms actually existed, or at least a lot of them, not all of them existed back then. So yeah, that's a good question though. We will see more of that. Yeah. Okay, so to maybe add a little bit of a twist here, we're not just going to be adding the input to the program itself, because there's not necessarily enough space in the buffer we're going to be writing to contain, well, we're not going to be writing it directly here inside the input. We're actually going to be inserting the malicious code in an environment variable, which is going to be pushed onto the stack above the return address, somewhere around the arguments to the main function itself. So remember when we executed, when we were using the exec syscall, one of the variants of exec was environment p and BP. So when our program runs, it's going to have a set of environment variables exposed to it, and we're going to replace one of those environment variables or insert into the environment some malicious code that we're then going to modify the return address to jump to and execute. So we're not just following this simpler model here, we're going to actually be injecting the malicious code into this environment variable and then modifying the return address to jump to it. So one of the mechanisms that I mentioned earlier to prevent against this sort of attack, which we will have to disable, are known as stack canaries. So has anyone heard of the saying a canary in a coal mine? I think I might have mentioned this last lecture, or to some students at least. Now, can someone explain it to me, where it comes from?
So canaries being smaller animals are going to be more sensitive to environmental pollutants. So if you were in an environment like a coal mine where you could have like a gas leak or some other sudden toxic, then you would notice because the canary would grow sick or die.
Yeah, exactly. So the canary would perish or go very ill or stop, maybe just stop singing. And then the miners in the coal mines would notice this and they would leave the mine because they knew it was dangerous. Likewise here, we have a stack canary, which is going to be some special value inserted just after the return address. And if this value is modified, the program knows that something malicious is happening, or perhaps the program just has been corrupted in some way, and it's going to execute prematurely. The operating system is going to terminate it. So in order for our exploit here to work, we're going to have to disable stack canaries. Another wrinkle is that on modern machines, code in the stack is not made executable by default. So to protect against these sorts of exploits, any code that is in the stack, any memory, any instructions that are in the stack segment of memory cannot be executed. So we're going to have to enable executable stacks as well. That's the second thing we have to change. Yeah.
So if we were doing this to like someone else, we would need to like enable the same stuff on their device.
If you wanted to do this to someone else, you probably couldn't do this directly as here. You'd have to either A, disable it first in their device, or B, you'd have to take a totally different approach to exploiting their machine, which is called return-oriented programming, in which on modern machines, let me introduce the last mechanism, then I'll explain what return-oriented programming is. The last mechanism is address-based layout randomization, which I think I might have mentioned before. Basically, the address of functions in the stack will be random every time you run your program. I think I demonstrated this in the previous lecture. I had that variable, that program that just printed the address of a variable. Every time I ran it, the address was different. That's the last of the three mechanisms we have to disable that protects against these sorts of exploits. Now, in modern cyber exploitation, attackers, to get around all of these sorts of protections, what they do is something called return-oriented programming, in which they modify the return address to not jump to some malicious code they've injected, but rather some part of the operating system's internal code. So like syscalls, for instance, which have to be at fixed memory addresses. Programs expect them to be at fixed memory addresses. And so they're not randomized. And they're also safe to go to because they have to be safe to go to because they're inside the kernel. And so attackers are able to cleverly weave together a bunch of calls to these different kernel functions and to create what are known as widgets. And with all these widgets, they can basically string together some arbitrary execution of code to exploit your machine or do whatever they want. Now, it's very hard to do that, but attackers have managed to be able to do this. And if you want to learn more, there are security classes at UCF you can take which will go into more detail. But that's the big idea. Okay, so yeah, those are the three things we're going to be disabling. So executable stacks or non-executable stacks, we have to enable that. Address-based layout randomization and stack canaries. We have to disable those as well. So now for the rest of this lecture, I'm going to walk through an example of how we can actually realize this exploit. Before we get started, you can probably just take attendance. So I'll just open up the UCF here now, and I'll pause the recording. All right, so now let's take a look at this example. First, I'll show you the contents of this directory we're in. Actually, remove that a.out file. So what we're going to be doing is basically executing that illustration I showed earlier, where we're going to be exploiting a program to obtain a root shell by injecting some evil code into an environment variable and then modifying a return address of some C program to start executing that malicious code. So this is all wrapped up in a Docker container. So I don't know if any of you have used Docker before, but it's a way to virtualize a machine. So you can run a virtual instance of a Linux machine in your own computer with Docker, and then basically wraps up all the dependencies, the operating system, everything all in one package. So it makes it easy for us to reproduce this exploit. One thing that I'll point out before we really begin, we have to understand one more system call. So there's one system call that I haven't shown you all yet, which we have to talk about, which is called setUID. So what setUID does is it changes the effective ID that a process is running with, and the process starts with what's called a real user ID. So if I were to look at a process, well actually I guess I could just run this tool to show you here. When a process starts, it runs with the privileges of the real ID, which is the owner of the file, the one who created it. Some processes, however, they need to run with a different effective ID, the ID of a root user, for instance. So for example, the sudo program, sudo, I don't know if any of you have used that before, but in order to do things like change the access mode of a file, you often need, well, sometimes you need sudo, which gives you super user privileges temporarily. So sudo is a program that needs to be able to be run as root, even if the user running it is not already root. I'm trying to think of an example of a sudo program I could run. What? Sure. I could just say like sudo apt install. So I could install a program using this command because I'm prefixing it with sudo. But I'm not a super user. I'm just my user, bpapis. So some programs need to have that super user privileges in order to execute correctly, and so basically they need to be able to change their privileges while they're running. Now to do this, what needs to be done is we need to set the setUserID bit on a program. And first what I'll do is compile this code here, the setUID program, print ID, and if I run it, you can see it tells me that my real user ID, the one who created this file, is 1000. That's my user ID, 1000. The effective user ID, the ID of the user whose privileges it runs with, is 1000. And then in the program itself, what we do is call this setUID bit to change the privileges of the user of this program to the privileges of the owner of the file, the one who created this compile binary. Afterwards, we print the user ID after calling setUID and then before calling setEUID. So running this here, it doesn't change anything because I'm the owner of the program, and we're setting the user ID to the effective user ID to the owner of the program. So it's going to be the same. But if I modify this program to give it the turn on the setUID bit, and then run it. Oops, actually I did this for the wrong thing. I should have given this to print UID, print ID. Oh yeah, it'll still be the same because I'm still the owner. But if I also change the owner of this program, so change owner, print ID, change owner root, print ID. So I need a sudo access for this, so this is a good example. I need sudo access to do this. I'm changing the owner of this compile binary to be the root user. And now if I run print ID, you can see, actually I have to, hold on. U plus S, print ID. There we go. All right, so now let's run this, print ID. Okay, now we can see the one who created this file was my user. I'm the one who ran GCC to compile this binary, print ID. But I made the owner with that change owner call that I called earlier, chown. I set the owner of the binary to root. But after calling set EUID, I changed the owner of the file back to the effective user ID of the program as it's running to my user. So again, we're getting RUID here, getting the user ID of the user who created this file, and actually we're doing that here. And then down here we're actually setting the effective user ID, the ID of the user whose privileges this process should be running under, to that of the user who created the file. So even though the owner of the file I had previously set to be root, after that call to set EUID, it's set back to my user, the one who created the file. Now that's all to say, some programs on your machine need to have the set UID bit set, and they need to have the owner to be root. That way they can run as root. And we can actually see this. So if I run ls-l here, you can see these. So I accidentally set the owner for, or the set UID bit for this file. I actually turned it off here. Change mode u minus s, set uid.c. All right. For some reason, my terminal likes to print binaries with the set UID bit set as red. And you can see here in the privileges, instead of x, which you normally see at this position, so here we normally see RWX, rewrite execute. Instead, we see S, which shows that the set user ID bit has been set. And the owner of this file is root, which means this file, when it's run, will run as root, with root privileges. And we can actually find all the binaries on our machine that have this set UID bit set by creating a pipeline. Oops. And actually run a script here to make this prompt smaller. So we could do ls user bin, see all of our binaries, add the -l flag here to view the permissions, and then we can actually pipe this to grep to find all the programs that have to run with the set UID bit set. And we can see sudo is in fact on here. It's owned by root and has the set UID bit set, so it runs as root. So in order for our exploit to work, we're going to have to exploit a program with the set UID bit set so that it has root privileges. Otherwise, we'll get a shell without root access. So another wrinkle, another prerequisite for this exploit to be as maximally powerful as it could be, you have to target a binary which already has the set UID bit set for it. Okay, so that's all the context, I think, that we need to start executing this. So I'm going to start going through this README step by step to execute this attack. So I've already built the Docker image. It takes a while, so I did that beforehand. We're going to run Docker. It needs to be privileged for this to work, so I'm going to run it here. Now we're in our Docker container. We'll cd into the home directory where this attack exists. And what we're going to be exploiting is this program called classic, like the classic version of this exploit. So if we look at this, classic.c, actually put this here. It tells us that in order for this to work, we need to have no stack protector, no stack canary. We need to have an executable stack. And we also need to disable address space layout randomization with this command here, which we'll do later. And all this program does is printf, try to exec then sh. It taunts us to try and get a shell working. And then declares a buffer of size 80, an integer variable r, and then does a classic buffer overread where we read 400 bytes into the buffer. So simple example, trivial example, real world code would obviously, hopefully not have this issue, but it's enough for us to just demonstrate the exploit. And then it just prints red number of bytes, no shell for you, and then returns. Now, if we succeed in exploiting this code, after this return is executed, we'll jump to the malicious code that we will have inserted in this environment variable. So that's the goal. Okay, so now let's make all these programs. So we'll create the compile binaries. There's a lot of warnings, we can ignore them. And we'll notice that this classic binary does have the set UID bit set. So if I do ls-l classic, you can see it has the set UID bit set for this binary. So it has root privileges. And now what we're going to do is first, to actually conduct this exploit, we need to create a sequence of, well, first let's demo smashing the stack and overwriting it. And we'll do that by creating a sequence of characters using this Python script here. So normal.py, all this does is just print a sequence of 400A characters. That's all it does. So what we're going to see now is just how we can, as a demonstration, how we can actually inspect the stack and the register values while the program is running using the GNU debugger. And we're going to feed this bad input here, this clear override of input to the stack to see this, to the program to see this. And after running this, you can see we just have normal.txt containing 400 letter A's. So we're going to run GDB. And this is the GNU debugger. We're going to set a breakpoint to tell our program to stop execution at line 13. And what is line 13? Well, let's see here, right here, the return address. So it's right before the return executes. We're going to stop execution of the program and have access to view the program stack and its registers and memory and so on. So I'll close this other window here. And now we're going to run the program, feeding it normal.txt. So this is going to be GDB syntax for running the program. The R stands for run. And we're going to be reading in with that redirection operator the contents of normal.txt, which is 400 letter A's. And we can see, I'll make this a little bit smaller so you can maybe see it better. We get a view of the stack. And we can see the stack is filled with the letter A because we fed 400 letter A's into the stack, into the program with that buffer overread. We can inspect this more with this command info frame. And if we actually look at the value of RIP, the instruction pointer, we can see the saved RIP is actually set to 0x41414141. Can anyone guess what 41 is? It's a hex number, 0x41. What is 41 in hex and decimal?
Not just 41? Oh, no, there it is.
So the first digit's going to be 4 times 16, 65. And what is 65? A. It's ASCII for the capital letter A. So we've managed to overwrite the return address to be the letter A, a bunch of letter A's, which right now is just garbage. It doesn't mean anything. But it shows us that we can overwrite the return address and successfully inspect the memory addresses here and see that it's working. So it seems like we have some vulnerability that we can exploit. So I'm going to quit the GNU debugger here. Now we're going to try doing this again with the actual classic binary. I think the last time we did the debug binary. So here we get a segfault. We didn't set a breakpoint. So the program segfaulted right away because we did manage to change the return address. But again, we changed it to just 414141. So the program just crashes. Now we're going to actually identify the vulnerability, the weak point in this program, or I'm sorry, to identify the return address, where the return address is. We're going to run this command here, pattern create, which is, this comes with GDB, and it will actually create a pattern of 400 characters long and write the results to pattern.txt. And we're going to use this pattern to identify the address, the return address of the function. or the address of the return address, where the return address is in memory. And then if we read this, if we run the program now with this pattern being fed to it, we can see that the stack here contains this circular pattern. It's kind of hard to read it. It's like a lot of garble nonsense, it looks like, but it is a circular pattern. And we can inspect the value of RSP and see that the return address the value of RSP stores this memory address, and at this memory address there is this value, 4141371. So this is the address that RSP stores. This is the address that we're going to be jumping to. Yeah.
So right now you're creating a pointer to the malicious text file?
Right now we're creating a
Or like new return, like
we created a malicious input which has a circular pattern in it. We're going to use that. There's some scripts we can use to do this. We're going to use that to identify where the return address is, the actual address of the return address, so we can actually find out how we're able to overwrite it. And so this is important for the later scripting we're going to be using, this address that is stored in RSP. And this X just means examine, W means examine the words, and this X means in hex format. So that's why we see this in a hex format. So this address here is important for our exploit to work, but the problem is, if I were to run these steps again, let me actually copy this value here, just make sure I've got it. I think this will do what I think it will do. Read in the pattern. Oh, well, I think I forgot to turn this back on. But what would happen if you didn't have address-based layout randomization disabled, if you had it turned on, this address would change every time. But I think I already disabled it before doing this demonstration. I forgot to re-enable it. That's bad. I should re-enable it. But since it's disabled, this will be the same every single time. And let me just verify that that wasn't a fluke and that it is disabled. I can do that by catting out the contents of this file here. Yeah, it's set to 0. So this file, randomize VA space, virtual address space. If it's set to 0, then ASLR is turned off on your machine. We want to leave it turned off for this example, but I have to turn that back on to 1 when I'm done. So we'll leave that off for now, though. Okay, so what we'll do is copy this address. So this is the address stored in the RSP register. We'll take this, and there's a script we can use. Actually, pattern offset. We can use this command with GDB to find the offset, I think from the base pointer, at which this value lies, and we see that it's 104. So this, for some reason, these numbers are always the same on my machine. It will not be the same if you run it on your machine. These numbers will be different. But basically, the return address is at offset 104. Now we can do Python 2. There's a script here that's given to us. I'll open this up. Find, put the GDB, find IP. What this will do is write a sequence of letter A's to a file, followed by a sequence of letter B's, that's what 0x42 is, packed together, followed by a sequence of letter C's. And the total payload length here is going to be 400 bytes, but we're only providing 1, 2, 3, 4, 5, 6 letter B's. The total would be 398 bytes, so we're going to have 2 extra null bytes appended here. So we're going to run this script. I want to run this now. Python 2 findip.py. It creates a file, findip.txt, which I'll open in Vim here. You can see we have all the letter A's, the letter B's, the 2 null byte characters that I mentioned, and then all these letter C's. And so visually what we're doing here is we're going to be using these letter B's to find to help us insert this return address here, just to verify that we are overwriting the correct area memory where the return address lies. So we're not going to be doing the exploit yet. This example here is just showing us that we can overwrite the specific address in memory where the return address is with some other arbitrary value. Really, what we want to see is that there's a bunch of A's followed by a B's in the return address and then a bunch of C's. That's what we want to see here. So we're going to pass this to the program again, this new input. GDB classic. So we get a seg fault, so it seems like something was interrupted, and we can see in the stack there's a letter C a bunch of times. Here there seems to be a lot of letter A's, which the RBP comes below the return address. So it seems like this is correct so far. If RBP is here and C is on the rest of the stack, that seems correct. And the actual instruction pointer is going to be at letter B. So that's because we had returned. This is the code ran had a seg fault. We had just executed the return. So the value of our IP should be whatever the return address jumped to, and it jumped to the letter B. And we can actually inspect this again more deeply with this command here, the examine command. Oops, $sign. And it says cannot access memory at address 0x424242. So we successfully overridden the instruction pointer with 424242, which is 6 instances of the letter B concatenated together. So we are able to overwrite specifically the return address of a program to point to some arbitrary value we've set. So in the last example here, what we're going to do is first insert into our environment variables the malicious code we want to execute. And then we're going to basically run another variant of that find IP script that we were looking at here. We're going to run a different version of the script, which instead of inserting some letter B's, it inserts the address of our malicious code that we're going to be injecting. So first we'll actually set the environment variable containing our malicious code. We'll do it with this command here, which will actually print out the bytes sequence, so the actual bytes necessary for this malicious shell code we want to run. What this code will do is basically just execute a shell. And for us to see what this looks like, I'm going to skip this command here and go on to this one. We can actually echo out the contents of this variable we just set here. So we set this environment variable pwn to the byte sequence for the malicious code to run a shell. We're going to echo out the contents of this variable. I'll do that first without any other stuff going on. We can see it's not really readable because it's just raw bytes. And we'll pass this to this ndisassemb command, which will disassemble that code into assembly code. So we can see the actual assembly code we're going to be injecting into our program. And this is what we're going to be trying to modify our return address to jump to the beginning of. So if our evil code is in this environment variable, we're overwriting the return address here to jump to the address at which this malicious code is going to lie. And so to get that address, we have one more script we need to run. Exploit.py. And here we're actually going to set the address of the instruction pointer for it to jump to. Now we're packing this with 104 letter A's because the offset that we found from the return address to the environment variable was 104. With the previous one of the scripts we were in, we were able to find that number, 104. And then we're actually setting the value at that 104 offset to the address at which the next the malicious code will run. Now we have to run another script to get that address, so I'm not going to go into this in too much detail. But this is actually a C program. And what this actually will get you is the offset or the the offset from the base pointer, I believe, at which the environment variables will begin, which will tell you where we need to set the RSP to, or the instruction pointer to actually run our malicious code. Yeah.
If you were like hacking on your own, would you have to make all of this from scratch, or is there like man pages for hackers?
So there is a tool called Metasploit. That's a Python library you can install, and it basically is just a catalog of all these different attacks for different machines, ready for you to just use. So a lot of attacks, I mean, a lot of antivirus software is really just an enumeration of existing attacks, and then it just looks for existing attacks in your machine, and then just detects them and tells you about them. But if you actually want to write your own attacks, I mean, that's a very difficult job, but it's also a very lucrative job, and perhaps. I mean, I know, like, supposedly 0 days, as they're called, 0-day attacks, which are attacks that have not been discovered before, they can sell for like millions of dollars. Because once they're used once, they're done. You can't really use them anymore because people are going to start writing antivirus checks for them. So. Okay, so we have the offset. We have the return address. We know where it is. We have the offset from that, or from the base pointer, I should say, at which our malicious code will begin. So now we're going to run one more script here, this exploit.py script. Actually, before we do that, let's just make sure we have the correct address here. So run GDB again. We're going to feed it our pattern. Oops. Pattern.txt, get a segfault, and pattern offset. This value should be at what the value in RSP points to, and it's an offset 104, so this is good. So the offset's correct, and then what we have to do next is just make sure the instruction pointer, the offset for the instruction pointer is correct, the address of the instruction pointer. Oops. Classic find ip.txt. Oops. GDB, not GBD. Okay, and then XWX RIP. All right. Yeah, so that's the value here. Where was the address printed? We had this earlier. Oh yeah, that's what we had to do. All right, pattern.txt /wx RSP. Yeah, that's it. I think this is it. Did that change? Where was that script? Git, this one right here. Yeah, this is the one I was trying to find. Okay. Oops. Sorry. All right, undo all that. Go back to where we were. Okay. Yeah, okay. All right, sorry, just trying to go through these instructions. Okay, so if we run this, it will tell us the address at which the malicious code will be. So now we have to plug this in to the exploit.py script that we have, so we can see it's a different value, so we have to change this. It was EE, I believe, 08 EE. Yeah, that seems to be correct. So now what this will do is pack in 104 letter A's, that's the offset to get to the environment pointer, or get to the return address. And then we overwrite the return address with the address here, which will be the address to actually jump to this malicious code. So now we can actually run this to create the exploit.txt. I don't think we have to run these. I think Classic already has these permissions set. Now if we run this program, it says no shell for you, but if I did this correctly, yeah, if I type ls, you can see we actually have a shell working. And more than that, not only do we have a shell, but if I type in who am I for the who am I command, what user I have, I am the root user. So I have root access. So I know it's a lot of different steps, a lot of moving pieces. But again, this lecture is supplemental, and I would encourage you to walk through this on your own, one step at a time. Yeah, I've kind of condensed a lot of material into this, tried to in this one lecture. Yeah. So do you have any questions? I know it's kind of like a lot of different steps, but yeah, or no, yeah.
So following this is like supplemental, which means it'd be good for us to like practice what we're learning.
If you're interested in exploitation or security, then it would be good to learn how to do this. There's one company, for instance, that I interned at one summer, Trail of Bits. Oh yeah, this is a blog post that I wrote for them. Yeah, I had to write a blog post as an intern. But this company, Trail of Bits, is a security company based in New York. They're like a very big security company, or not. Actually, they're very small, but they're very like prestigious, I guess. And this is the kind of stuff they work in, like security. So, and binary analysis, like assembly analysis, things like that, and like auditing code. So if you're interested in security, you could potentially work for a company like this. That's like one career path. Granted, I worked for them. I was working on their compiler team, not on their security team, actually. So. Okay, so no questions, I guess. Any questions at all? I mean, I know it's probably kind of confusing. I know I kind of stumbled through it at some points, but it's challenge. There's a lot of moving pieces to these. Yeah.
You mentioned address randomization. What exactly does that do?
So memory is virtualized. Memory is not. You don't actually write directly to your RAM. That would be bad for a number of reasons, because one program could then have free range to access and modify the contents or the memory of another process as it's running. So instead, for security reasons and other reasons as well, memory is virtualized, so it's actually, each process is given the illusion of full access to memory when it really doesn't. Every read to memory goes through the operating system first. And what the operating system does is randomize the mapping between virtual addresses to physical addresses on the actual RAM. Now, I encourage you to read if you're interested in this. I know it's kind of a lot I'm not going to go into too much detail because this is like a very deep topic. But I recommend reading this book, the O-Step book, Operating Systems in 3 Easy Pieces. I mentioned it before. Specifically, if you want to know about address spaces, you can look at this section right here, this third column in this table. This will tell you all about how memory virtualization works, and it actually explains address space layout randomization for you. It's, again, another security measure. You can see how the operating system actually works with the hardware to make this real. So yeah, good question. We've already actually kind of seen another example of virtualization before in this class, processes. So you know that processes, the processes, idea of a process, a running program, is really just an abstraction. We could just load a process into memory, set the instruction counter, the instruction pointer, to the beginning of that process's instruction set, and then just let the CPU run the process directly. But we don't do that because it prevents us from running multiple processes at the same time. It lets the process have elevated permission to do potentially bad things. By having this abstraction of a process, we can actually save and restore the state of processes, run different processes at different times, maybe run them concurrently, all sorts of things we can do without abstraction. And similarly, memory is virtualized as well on a machine. So this whole section in orange is on virtualization for that reason. Yeah. Oh, that's a way of giving programs priority to run when you have more than one process running on your machine. So this is one of the older techniques that are used that they describe in this textbook about how to schedule processes to run when you have multiple processes competing to run, wanting to run on the same one CPU.
So that's like a thing where it's like you'll have like if you have like a split screen, it's like not running them at the same time.
Yeah, for instance, that's one example. They're not actually running at the same time. Now, if you have multiple cores, they might actually be running at the same time. But if you don't have multiple cores, then they're not really running at the same time. They're, you have the illusion of them running simultaneously. Okay, but that's it for this lecture. So if you have more questions, you can stay after class and ask me. In the next lecture, we'll be going over the final review. Make sure to come to that one, and I'll see you all then.